Okay, folks, maybe we could make a start, and if we get going, we'll finish sooner. I guess last time we were talking about Ampere's law and working out magnetic field, and I think one of the examples we looked at was a loop and working out the magnetic field at the center of that loop. We did an arc, and we figured out the magnetic field due to the arc, and I said if the whole loop, it's just an extended arc. So for a loop, and by a loop of wire, I basically mean clearly some wire coming in, it loops around on itself in a circle, and I'm looking at the magnetic field at the center of that wire. So this is a current carrying wire, there's a current flowing through the wire, and if I say there's a positive current flowing in that direction, and it flows around the loop, I guess in an anti-clockwise direction, and then comes out again, the magnetic field at the center of that loop is just like an arc that's 2 pi in length, because we worked out an arc, we worked out part of a loop. So what we looked at last time was the magnetic field for the loop was mu naught I over 2 times R. Where R is the radius of the loop. And we argued that the field round the wire is a series of concentric circles, and if I bend that wire around, all the field at the center is going to be enhanced. And you know the direction of the magnetic field at the center of this loop. It's going to be out of the board, yeah. It's right-handed, so it's a positive current. Current is going around this way. The magnetic field round the wire is going to point out into the room. So all the field on the inside of the wire gets channeled into that loop and gets amplified. And we argued that was a way of creating more magnetic field. But let's look at an example. So we know what mu naught is. Four pi times 10 to the negative 7. Good. It's also in your calculator if you don't remember it. So let's assume a current of 1 amp. So that's relatively large current to be flowing through a wire. And let's a radius of 1 centimeter. And that's all we need. So we plug mu naught I and R into there, and we get a magnetic field of 6 times 10 to the minus 6 Tesla. So, is that a big magnetic field or a small magnetic field? Yeah, it's a small number. Clearly it's 10 to the minus 6. But we always like to do things relatively. So the magnetic field due to the Earth is, well, it's more than this actually. So B for the Earth is the order of 20 to 40 times 10 to the minus 6 Tesla. A few tens of millitesla. It depends where you measure. It also depends on the orientation. So there's a range there. So a large current through a wire is still producing a magnetic field that's small compared to the size of the Earth. So what could we do? Well, we could increase the current. That would increase. But then that's going to cause more energy or cost more energy to drive the current, and eventually we're going to melt the wire if we put too much current through, because there'll be always some resistive heating. We could make a smaller radius. That would clearly increase R. But then I guess the smaller the radius, the smaller the wire we need to bend the wire through that radius. So there's a trade-off between resistance there as well. So, any other solutions?
More loops.
More loops. I just repeat the process, more and more loops. And I stack up the number of loops. So what I want to do today is analyze that structure of more loops, which we call a solenoid. It's basically a wire that we curl round into a spiral, and we just add many, many turns of the wire. And we call it a solenoid. So I want to look at the magnetic field And solenoid is just a technical term for a wire that's curved into many loops. So if you want to try and draw that, it would just be a wire that I then wrap into multiple loops. And I drive a current into that. And if the current is going the same way in each loop, so it's going counterclockwise, the same way as that one in this example, doesn't matter. I could argue that for each loop, I'm going to generate that amount of magnetic field. That's one loop. And the direction is going to be the same because of the right-handed rule. The current around each loop is going in the same direction, so the magnetic field generated by each loop must be in the same direction. Magnetic field is a vector. So to work out the total magnetic field, we add up the vectors. So they're all pointing in the same direction, so they're all going to add up to give me a bigger magnetic field. So we can analyze that structure using Ampere's law and quickly come to prove that that indeed is the case, that we amplify the magnetic field, and then come up with a simple expression for the size of the magnetic field. So let's take this example off. Now let's draw another diagram. Let's take a pair of scissors, cut this through the center to give me a cross section of what that looks like. So if I took a cross section of this thing, what would I see? Well, I'd see the wires, I'd see the bottom wires, and I'll pack them so close together that they're all touching along the bottom, and I'd see the top wire here. So clearly these wires are connected. So it's a circle, and I've cut it along this plane. This is the top wire. The current will flow out of the top, back into the bottom, and round through the next loop. So clearly I've taken this corkscrew, and I've cut it along the two axes. Okay, so let's assume the current is coming out of the top. So I'll draw dots here. So this is I. It's coming out of the top, flowing round this half plane and back into the bottom. So these are the wires, and these dots are the current out of the board or page, and here the current is going back in. So I could argue that if the current is going into the bottom around one of these wires, I could imagine there's a circular magnetic field, and it's going to follow the right-hand rule. So each of these wires is going to have a magnetic field flowing around it. Or if I took one wire, current flowing in. Current coming out of the top is going to be coming in this sense. The magnetic field is going to point in this direction. So if I look at the magnetic field just at the edge of the structure, I could argue that as the field comes out, as the wire comes out, the current comes out of the wire in this direction, the magnetic field is going to curve that way and is going to point along the center. Likewise, the current going into the wire here is going that way. Right-handed rule tells me that the field is going to point in this direction. Okay? So I could argue that the magnetic field, we can try a different color. So I could imagine that B field would get confined along this direction. That's only applying this right-hand rule and arguing that it should definitely point that direction. The form of it we may not definitely know. But we know those magnetic field lines have to either start or end on a north pole, or they have to form a complete loop if they're in free space. So essentially these things would have to loop around outside and come back in. So how can we use Ampere's law to figure out what the field is? Well, Ampere's law was we walked around the circumference of a shape, any shape, and we did B dot ds. We added up all the segments of magnetic field along the outside of that wire relative to the direction we were walking in, and that would give us the total. We could use that to work out the total magnetic field, because that was related to the current enclosed by the wire. So we're going to apply Ampere's law, and that basically says, this is one that you should remember, the integral of B dot ds is mu naught I enclosed. So if we draw a loop of a loop somewhere, we capture all the current, or we lasso a certain part of this, we can use this expression to perhaps work out the magnetic field. So we need to choose our loop, and the loop we're going to choose is similar to something we've looked at before, but let's choose a rectangular loop. And let's call the corners A, B, C, and D. So Ampere's law, written in red, tells me that if I walk around this red loop and do E dot ds on each bit of that loop, the product of that equals mu naught times the current enclosed by that loop. Okay, so all I have to work out is that integral and what the current enclosed by the loop is. So let's make a couple of definitions. Let's say that the current in each wire equals I in one wire. It's the same wire, it just loops round and round. So the current in the wire is I. We'll call the length of this side H. So the distance from A to B or from C to D, top surface and the bottom surface are going to have the same length, which we'll call H. And we need to know how many times the wire loops through that box. So we're going to say the number of turns per unit length. The number of times the wire makes a complete loop in a certain length is going to be the number of loops. So we'll define N. So we define N as equal to the number of turns of wire. Basically, that's the number of times I've wrapped the wire around per unit length. So it's per unit length. Okay, so if H is my unit length, the number of turns per wire in this solenoid is 1, 2, 3, 4, 5, 6, 7. 7 turns per that length. Usually the length is a centimeter or a meter, and you'd have maybe hundreds, thousands, or tens of thousands of turns of wire. You'd wrap a thin wire many, many times round the outside of the solenoid to form the solenoid. So that's what we mean by turns of wire. Okay, so how are we going to do this integral? Well, we've got a rectangular box, and it's obvious in that box the magnetic field direction is going to be different on the different sizes. So in the ends, I'm going to integrate up the end, and the magnetic field is going to point along the center. So B dot ds is going to be 0 on the end. B is that way. ds is my trip around the wire. So ds, remember, would be an element along the direction I walk around the wire, and I'll walk around clockwise. So if ds is here, in this section, B and ds are going to be parallel. So cos of 0 is 1. So that's going to add up. So I'm going to use symmetry. That's why I've chosen this shape. So I'll break this integral into 4, and I'll do each wire, each edge separately. So let's go integral from A to B of B dot ds plus the integral from B to C of B dot ds plus the integral from C to D of B dot ds plus the integral from D back to the beginning of B dot ds. And I know all that is mu naught current enclosed. So let's expand the equation. We'll just write down each of those terms. So now you're becoming an expert at doing this type of integral. So the first one is going to be, I'm going to assume B is constant. And it's going to be multiplied by, well, we're doing ds, but we define the distance as h in this case. So let's say h is the distance. So it's going to be b times h. Okay? So that'll be b h for that segment. Okay, so I've made an assumption that I've got uniform magnetic field. I can take that out of the integral. I have same direction, so I get rid of the cosine, take the b out, integrate along ds is the length of the loop. What about B to C? 0, because I'm at right angles. What about this one? So 0, somebody's reading ahead. No, it's negative 0. This is the one where we have to make an assumption. And this causes a little trouble conceptually. It certainly caused me trouble when I came across it. We're going to assume the magnetic field outside the wire is small. And if we make the center very narrow, all the field lines that are propagating along are flowing through the center of this solenoid. Where do they have to go? They have to loop round, and they have to go back and come in here. So what's the size of the space up here? It's infinite. Goes on forever. So the magnetic field along the center of this axis will go off to infinity and reappear at minus infinity as a straight line. So this is minus infinity, this is plus infinity. All the other ones will have some curvature. So the density of magnetic field lines out here is low. Okay, so I've taken the magnetic field lines in all space and I've focused them through this little tube that maybe has a centimeter in cross section. So I'm arguing that the magnetic field along the center is very much bigger than the magnetic field in all space round about. Seem reasonable? Some people are looking doubtful. So if this is infinite in both directions, I could argue the magnetic field is so small that I'm going to call it 0 outside. So if I measure a magnetic field at any point outside, it's going to be so small because I've spread those field lines out so far. So I'm going to assume B is 0 outside. So B up here is 0, or if you'd prefer, approximately 0. So when I do the integral along the top side here from C to D, I'm going to assume that the magnetic field at that point is 0. So if B is 0, the integral of B dot ds is 0, so I can get rid of that. I could also argue it, I could look at it another way. If I make this line close to the top of the wire, I've spread the field out in all space up above. The magnetic field is spread off over all the space up above. The bit along that line must be very, very small. Must be hardly any field along that wire. And this is a pretty good approximation when I've got a long solenoid. If I've got many turns, and most solenoids will have hundreds or thousands of loops of wire, that's a reasonably good approximation. If I've got one loop of wire or maybe two loops of wire, that's probably not a good approximation, and you probably want to redo this with maybe a circle or some other way of analyzing it. But for a long wire, this is a reasonably good approximation. So that leaves me finally just the integral down this side. And if the integral up this end is 0, the integral down here, all the fields penetrating or going along this line, the field line and the direction of integration are at 90 degrees, so that component would be 0. Which is why I chose this box in this configuration. The only contribution is along the center of the solenoid. So what's the current enclosed? Well, I'm defining number of turns per length. All right, that's the number of times the wire wraps round. I know my length is h. So the total number of times the current loops through is just h times n. So h times n is the number of times the current passes through. So the total current enclosed by this box is the current in one wire times n times h. And I also need to multiply by mu naught. So that equals mu naught current in one wire times n times h. And that explains why I set up number of turns per unit length, because I've got h on this side, I've got an h on that side, and I can come up with an equation that basically says the magnetic field B, in this case, is mu naught I times n. So n is the number of turns per length. So if I take a wire, I can wrap it round many times. I can then overwrap. I can come back on top of those wires, and I come back on top again. So I can keep multiplying along the length. I can get many turns, but I can do multiple layers of turns. So I can build up a thick coil as multiple layers. So n in principle can be a huge number. N can be thousands, tens of thousands even, I guess. So you're multiplying the magnetic field every time the wire loops round. So this is how you generate an electromagnet or something that produces a large magnetic field. You have multiple turns, and you basically focus all the magnetic field lines into this center portion of the solenoid. You'll have some field lines that extend out, go around and come back in. So if you wanted to draw the whole thing, it looks maybe a bit like this, which begins to look like a bar magnet, a piece of magnetic material. It's got a north pole at one end, south pole at the other end. But I've created the magnetic field using the current. So if I turn off the current, I turn off the magnet. So it becomes an electromagnet, a useful device. And I can easily analyze that using Ampere's law to give me an estimate of what the magnetic field strength would be. Okay, questions? Okay, well, what I'm going to do in the rest of the lecture today is introduce the concept of induction, which should have been, I'm kind of half a lecture behind now, but I'm going slowly because this is kind of the more tricky part of the first section of the course. So let's do that by considering an experiment. And the experiment is that I take a loop of wire and I connect it to an external circuit. And this basically measures a current. So it's an ammeter. You've done the first lab, so you know what an ammeter is, a voltmeter, so you can measure current, you can measure voltage. So that's a sort of introduction to first principles. Now, thought experiment. If I replace the ammeter with a battery, the battery is going to drive a current round the wire. The current flowing through the wire is going to produce a magnetic field. and I know the direction of the magnetic field, and I can work out for a single loop what the magnetic field would look like. So Faraday argued then, well, okay, so if the current flowing in the wire generates a magnetic field, does a magnetic field applied to the loop generate a current in the wire? So an obvious question to ask. So he did a series of experiments. First experiment was easy. He just made the loop, connected to an ammeter, something that measures the flow of charge or flow of current. And in those days didn't know about electromagnets, so basically had a bar magnet, which had north pole at one end, south pole at the other end. Therefore a bunch of field lines coming out of the north pole, going into the south pole. So field lines kind of look like that. So that's the blue is the magnetic field. And he put the magnet in the coil, and what did he see? Sorry, yeah. Voltage, current. Well, actually, if you just put the magnet into the middle of this coil, what he actually saw was nothing. There was no current. So if I place a magnetic field around this loop, he saw no current, which surprised him. But he did notice that as he placed the magnet in to the loop, a current flowed. So as he pushed the magnet into the loop, there was some current. But when it was placed in the loop and stationary, there was no current. As he removed the magnet, the current went in the opposite direction. But then when the magnet stopped, the current stopped. So what does that tell us? It's not the magnetic field on its own that's causing the current. It's what? It's the change in magnetic field. It's dB by dt. The rate of change of magnetic field flowing through this loop is causing the current to flow. That's what he noticed. And if you move the magnet faster, what happened? More current. So if you move the magnet very rapidly, you'd see a bigger current. So the faster I move the magnet, the bigger the current I see. Of course, you're doing experiments, you want to explore all possibilities. I rotate the magnet the other way around, so south pole goes in. Again, as the magnet moved in, he saw a current. But when the south pole was going in first, the current was in the opposite sense to when the north pole went in. So the direction of the current flow depends on the direction of the magnetic field. And it depends on the speed at which I'm changing the magnetic field. So that's how these experiments were first derived, and that's what formed Faraday's law. His conclusions were, one, a current only appears when there is a relative motion. The magnet is moving, therefore the magnetic field lines are changing. Two, faster motion gave a bigger current. And three, changing polarity of the magnet changed current direction. Okay, so you notice three things. A current on the ammeter only appears when there's a relative motion of the magnet in and out of the loop. Move the magnet faster, got a bigger current on the ammeter. And if I flip the magnet round, I got the opposite flow of current. I got a negative or a positive. So those are Faraday's original observations. More formally, if we look at this, we're saying current here, and that's because original experiments he used an ammeter. If I generated a voltage in this circuit, what would happen? A voltage in a closed circuit will drive a current. So I could argue that I'm creating a voltage in the current, and that voltage in the circuit, and the voltage is creating a current. Ohm's law tells me that V equals IR. So if I've got a voltage, I drive a current. To have a current moving, I have to have a voltage. To have water flowing through a pipe, one end has to be higher than the other. So I have to have some pressure in the water system, or I have to have some potential energy or electrical potential. So actually what we know now to be true is this isn't really a current we're generating with the magnetic field. It's actually a voltage. And the voltage in turn generates the current because it acts like a battery. And I've got a closed loop of wire, so I move electrons. Okay. So let's see if we can use that to, those statements are useful, but they're more useful if I can actually make some sense of them with some sort of relationships that I can then use to design something in the future. So you can do the same type of experiment, or a similar type of experiment would be if I had a loop of wire, and I could make a number of turns. So this is the solenoid I had previously. And I connect that to a battery. So this is battery. That's going to drive a current through the wire. Connect the wire to the top and the bottom of battery. There's going to be a current flowing. That's going to produce a magnetic field in this little loop. If I place another loop of wire here, and connect it to a voltmeter this time, I would see a voltage, which is essentially the same as what Faraday did. But current may be easier to see. So if I turn the battery on, so if I put a switch in the wire, when I close the switch, if I measure the voltage, I would get a spike in the voltage when I close the switch, and that then would go back to zero. Because I've argued when there's a uniform current flowing in the wire, there's no induced current or induced voltage in that second wire. I have to be changing the magnetic field in the second loop to generate a voltage or a current. So we say that the induced current is caused by a voltage or we use the term electromotive force here, which basically means voltage. And it comes from these original experiments. There's some force that causes the current in the second loop or the voltage in the second loop. So there's some force that's moving the carriers or the charged current elements through the wire. So bits of current are flowing because there's some force. An electromotive force, which has units of volts. And we now call this volts. And it's interesting because the textbook still uses EMF induced in this section, which is what they called it in 1800 and whatever they did these experiments in, but we now call it voltage. So electromotive force for our purposes just now we'll just call voltage. So we're generating a voltage. And I know that the voltage, or E, which equals EMF, is given by Ohm's law. It's the current flowing times the resistance of the wire. V equals IR, we know that expression. So if I know the resistance of the loop, I know the current, then I know the voltage, so I can measure either of them. But from those experiments, what I notice is that E in the second loop, so I'm going to measure the voltage across the second loop. So this is loop 1, and this is loop 2. So the EMF, or the voltage induced in this second loop, is proportional to dB by dt. We argue that from the magnetic case. As I move the magnet, it's a changing magnetic field. Changing magnetic field with time is dB by dt. So the size of the voltage generated between these terminals, depending on dB dt. So I'm moving magnet in the first experiment, moving the magnet faster, dB by dt, rate of change is going to be bigger, so therefore it's going to be more voltage and hence more current. The other thing that you can do with these experiments is, if I make the size of loop 2 bigger, how do you think that might affect the voltage induced in loop 2? I'll make the loop much bigger. So I've got a constant magnetic field or changing magnetic field with a certain spatial distribution. If I make a bigger loop, what do I do? Oh, bigger. Do I get more or less magnetic field through the loop? No, if I make a bigger loop and I've got a set of magnetic field lines, so I've got a uniform magnetic field lines coming through this room. They're going from this board straight out there. If I use a little loop that's this size, I'm going to get this area times the magnetic field. If I use a big area, I'm going to get more magnetic field lines coming through that loop. So it turns out that the voltage on epsilon, the EMF on 2, is also proportional to the area of loop 2. So if I make this bigger, and I don't change this half of the experiment, I get more voltage. So what does this look like? Concept we've talked about in terms of electric field. Somebody over here said it. Flux. It's the flow of the field lines through a certain area. So this is telling me the answer is really dependent on flux, the flow of the magnetic field defined by a certain area or a certain region in space. Okay. So we need to make another definition. We need to define magnetic flux. And we do this in a similar way to the definition is the same, but in terms of practical applications, in Gauss's law we drew the flux through a three-dimensional closed surface. We put the charge in a box, closed the lid, and measured all the flux coming out or going in. That told me what was in the box. Magnetic field we know is slightly different because it's due to moving charges. So some of the concepts translate, others are modified and translate. We still define flux as the flow of magnetic field lines through an area. So it's defined the same way. So consider an area, and we can just draw a general area. Clearly we'll use a sphere or a square box or a flat surface at some point. And we can define the area vector as pointing normal to that. So if we take a flat surface, so just taking a piece of paper, cut to some arbitrary shape, and I'm looking at the flux through that surface. And maybe my magnetic field is coming at an angle. And we've got some angle theta in here. So we define magnetic flux in exactly the same way as we defined electrical flux. Phi b in this time is the integral of b dot ds. So essentially we're going to integrate over this area, i.e. we add up all the little components of b coming out of all the little boxes that we define across the surface. So if I've got a uniform magnetic field, B will be constant. If it's not parallel to dA, I'm going to have to say that this is equal to the integral of B ds cosine of theta. If B is uniform, I can come outside the direction, outside the integral. Cos theta is going to be uniform if it's a uniform direction, so it's a number. And the integral of ds is going to be the surface area. Question? Good point, yeah. You wrote it down correctly and then changed it. No, you should be calling these out, you see. I should be giving out extra credits on the exam for every time you spot one of these things. Now I'm going to check my notes, because the trouble is I can't read my notes without my glasses, and I can't see the wall with the glasses, so it's changing. So my notes are actually correct, it's just the interpretation. But we know a changing flux is what gives me the changing or the voltage in the field. So that allowed Faraday to come up or postulate, pulling all these things together, what we now call Faraday's law. So Faraday's law basically is written as the induced voltage, or EMF, electromotive force, the amount of voltage you measure on loop 2 over there, is equal to d phi b by dt. It's the changing flux through that area. So it's not just the magnetic field. The early experiments were magnetic field, but they didn't try and experiment with different loops. They only looked at changing magnetic fields. So it's a change of flux. There's a negative in front of this, which we'll talk about in a moment. This is actually due to Lenz's law. Lenz's law tells me, this is how I remember the direction of that induced current or induced EMF. Lenz's law says that the direction or the polarity of the voltage is such that it will generate a current that in turn will generate magnetic field, which will oppose the field that's generating it. That's a lot of words. It's the law of being lazy. You're in bed on Saturday morning, you don't want to get up. You want to stay in that energy state. So it's an effort to get out of bed. You have to do some work. So normally in physics, things like to be in a certain state, and often you have to apply energy to change them. So they like to get to the minimum energy state. So if I drop something on the floor, it stays on the floor. To remove it from that state, I have to lift it up. So I have to do work. So it's a manifestation of that. Basically, the negative sign comes from what we call now know as Lenz's law, which we'll talk about maybe next time. And that explains the direction of the current flow induced. You also see this written as negative d by dt of this thing, the integral, right, integral of b dot dA. What's this one? If I give you a charge in an electric field and ask you to work out the voltage, what do? You do E dot ds, and I integrate it from initial to final position. So this also equals the integral of E dot ds. So suddenly I'm producing these scary electromagnetic equations, but we now have some understanding of how they work. This is a chain, all this is flux. It's the flow of the magnetic field lines through the area. So the integral here tells me about the area or the flow of the magnetic field lines. This is voltage, or it tells me how to work out the work done in moving the charge. So this is the energy in moving the electric charge. So we know how to work that out, so we work this. So this was really the first connection between electric fields and magnetic fields being connected together. Up until this point, people thought magnetic fields came from magnets, and that was one thing. Electric fields came from static charges or currents, and that was another thing. They didn't put the two concepts together until Faraday started doing this type of stuff. And then Ampere and people started looking at magnetic fields around conductors. Or I guess all around the same sort of time. So what's this useful for? Generating current. What am I doing? I'm transferring energy here from here through free space to this circuit. So anybody got one of these phone chargers where you just put your phone on the pad? Maybe the Samsung before it went on fire. Oh, Samsung whatever number. Wasn't a relation to this, but basically that near field, that charging where you can just place your cell phone on top of a pad, it's induction. It's this rule of induction. Here I've got a constant current, so I get a constant magnetic field, so d phi b by dt is 0. But if I've got an alternating current, I've got an AC current that's going positive, negative in time, the direction of the current, and hence the voltage, are always changing. So the magnetic field generated by loop 1 is always changing. Therefore, the flux through loop 2 is always changing. So if I design my system, I'm going to induce an alternating current in loop 2. And that secondary loop will connect to my cell phone battery. So this is in your cell phone, and this bit is in the stand. You place them on top of each other. Energy is transferred from the stand to the cell phone. So it's not magic, it's just Faraday's law of induction. It's also used for generating electricity in power stations. Usually there's some fixed magnet and you've got a rotating coil or something. How does that work? Well, this is flux, which is this thing. So I could have constant, never changing B. So if I've got a constant magnetic field coming up here, only over a small area, and I take a loop with a certain area and I move the loop into the magnetic field, what's changing through the loop? the area, and hence the flux. So the flux depends on both the field and the area. So a uniform magnet, a loop that I move into and out of the magnetic field changes the flux through that loop, so I'll induce a current in that loop. So that's how you can generate electricity. Basically, you've got a magnetic field, you've got water turning a turbine, and that turbine's got lots of loops orientated in wires, like solenoids. Those loops are rotating through a constant magnetic field, and that generates a current in the loop, and that's what keeps the lights going. So it's got lots of applications, and it's a connection between magnetic fields and electric fields. So we'll pick this up again on Monday, and I'll talk about Lenz's law. I'll talk a bit more about this thing, why we've got the negative here, and how to work that bit out.